Welcome everyone to the BigML Object Detection Release webinar. We're excited to host all of you today. My name is Atakan Çetinsoy, VP of Predictive Applications for BigML. After I make an introduction to object detection in the business context, my colleague Charles Parker, VP of Machine Learning Algorithms, will be delivering today's demo and object detection product updates. So let's get started. Object detection is one of the pillars of modern computer vision, and it involves localizing and classifying usually multiple objects of interest in an image. The input can be photos, infrared or LiDAR type data, or still images derived from video footage, depending on the context involved. The objects being detected may also take many forms, such as vehicles, persons, animals, among other objects of interest. BigML object detection complements the recently launched image classification, generally available on the platform. Whereas image classification is concerned with assigning the right label or labels to a given image, as you can see here on the left. Object detection uses bounding boxes to identify the objects that belong to one of the predefined set of classes. The example on the right-hand side here showcases a city traffic scene with trucks, cars, traffic lights, and signs individually detected. If you look at the trends that are responsible for the rise of object detection in the commercial context, we see that the wide availability of camera equipment capturing images and video all around us is an important marker. Cameras in the retail stores, city streets, intersections, factory floors, or construction sites are not uncommon. Consequently, we have abundant image data. Next up, we have the success of new and advanced flavors of deep learning techniques, such as variations of convolutional neural nets, achieving performance levels previously hard to imagine with more traditional image processing approaches. Of course, these deep learning algorithms are pretty compute heavy, so migration of IT workloads to the cloud and the associated cost efficiencies due to high throughput GPUs have helped further promote object detection. Finally, I'd like to open parentheses for next generation machine learning platforms like BigML for drastically lowering the barriers to entry by making even sophisticated object detection techniques easily consumable by businesses large and small. In summary, the time is right for every business to seriously consider insight generation from their image data. With that intent, if we look around, we notice real-life use cases of object detection are indeed everywhere. For one, there are many productive uses of object detection in manufacturing. Quality control and defect detection is one such example that helps process engineers take corrective action upstream instead of downstream in the manufacturing process when it becomes much more costly to address defects with repairs. In retail, object detection also has lots of potential applications. One interesting example is analyzing video feeds in stores to constantly monitor shelves and automatically identify out-of-stock situations that may result in lost sales. In a typically low-margin business, depending on moving lots of product fast, this can go a long way. In agriculture and animal husbandry, valuable livestock can be counted and monitored to ensure their safety and even to detect disease early on based on their movement patterns. In the healthcare sector, disease diagnostics is one target use case for object detection, among many others. And the example we see here is a mammogram, which can be analyzed for different types of irregularities like benign or malignant tumors. State-of-the-art object detection systems have already matched and even exceeded human expert performance in some of those tasks. Professional sports franchises and collegiate teams have rich image data sets that can be fed to deep learning models to analyze in-game player positions, spacing, and overall performance as a decision-making tool for coaches taking the Moneyball approach to their profession. Last but not the least, transportation use cases include monitoring different types of vehicles, pedestrians, and traffic conditions as part of smart city initiatives. Continuing with transportation, smart license plate recognition applications are becoming key operational enablers for infrastructure operators like toll road concessions. At BigML, we have implemented such a solution for a global company, and it involved cascading object detection tasks. As you can see here, the video feed data capturing hundreds or thousands of cars traveling is reduced to individual vehicles. Then a specialized object detection model places a bounding box around the license plate. Given the variety and the different types of vehicles on the road, this is not necessarily a trivial task either. And once the license plate is identified, the next object detection task is basically it involves dividing it up to read state names and the individual alphanumerics that make up the license plate itself to enable integrations with, for example, customer billing systems. This is a great example of a previously unsolvable problem being tackled by machine learning effectively to streamline operations and add value to the company bottom line. Another interesting use case we're currently tackling aims to prevent dangerous behavior by certain spectators at sports events and stadiums. It also features object detection as a key component of the solution. In this case, the target incidents for the automated monitoring system to pinpoint can take the form of inappropriate banners, flares, firearms, or racist symbols. The image processing models are being trained to detect those object classes by processing video footage, mainly from European soccer games at this point. And human security professionals can become much more productive when augmented by object detection capabilities filtered through anomaly detection coupled with clustering models. Performing object detection with traditional tools is not exactly a plug-and-play experience. You start with image data and typically have to find a labeling tool where a team of labelers draw bounding boxes around the objects of interest in your images for as long as it takes. And out of the labeling tool comes a metadata file and the images themselves that have to likely be uploaded to a separate open source type modeling tool. You hope that the labels generated in the labeling tool match the format expected in the modeling tool. If not, you have to build a script to do some data transformations. And at that point, your machine learning engineers can start creating models. The IT team gets involved to make sure that the modeling tool works without a glitch on your local hardware or a cloud service that your company uses. For instance, by making sure that the tech stack includes the GPU chips needed for your training jobs. And hopefully, you finally get to a good enough trained model that you now need to deploy to a separate machine or a virtual machine to make predictions in production. Your IT team may have to provision and configure a new dedicated machine for this activity as well. Assuming the predictions turn out successful and that management wants you to scale this whole thing up, which of course means many more models being trained in parallel and more infrastructure resources and more IT support to handle the extra workload. It doesn't stop there either, because you still need to monitor and maintain all these models and retrain them if and when they decay. What if there's an issue? Then you have to do some troubleshooting by tracing the faulty prediction back to the data set its model was trained on to reproduce the problem. And if you want to automate that whole process, you probably need to invest also in a separate machine learning ops operationalization tool, ML ops tool. It's quite a labyrinth of a process indeed. How could all this be handled better? Well, BigML simplifies it all for you, since it eliminates the need to jump from one specialty tool to another, along with all the IT headaches to keep the Band-Aid solution up and running. The BigML approach, it's all in one. You simply feed your image data to the platform once. The labelers label the data, which is immediately available to the machine learning engineers that can train either one-click or AutoML or configured custom models. All the infrastructure level concerns are abstracted away from the end users, thanks to our auto-deployable and auto-scaling backend. And it's a true team productivity booster that accelerates your time to market for machine learning projects. And it does so in a cost-efficient way with built-in machine learning workflow lifecycle management and performance monitoring capabilities. This may not be obvious to the uninitiated, but when implementing business solutions on top of BigML, you can also reach for higher order automation. For instance, the manual image labeling task can be further automated by first creating a custom semi-supervised learning workflow composed of multiple BigML resources. Then you can create a WizML script for your workflow, either in a single click with our Scriptify feature or by using the WizML editor. Now your custom image labeling workflow is coded once and can be shared with your work group many times over and be edited as a one-click action drop-down menu item on the BigML dashboard for any of your permissions. The resulting effect is a collection of more sophisticated machine learning workflows tackling difficult business problems without adding brittle band-aid designs that span multiple tools and are probably held together by glue code that itself needs to be constantly updated because the underlying tools and libraries constantly evolve. The BigML approach is akin to bringing to the platform perfectly fitting, well-engineered machine learning primitives one by one, just like the Lego pieces you see here, so that our users can pretty much build, automate, and if they see fit, share the blueprint for any predictive solution they can imagine. By virtue of the fact that object detection is now available as a native resource on the platform, it inherits all the things that make BigML image processing unique. To name a few, from labeling to inference, evaluation, predictions, users don't need to master multiple tools for different parts of the typical image processing workflow. We house it all, and all the activities of the image processing cycle is in a single place. Our composite sources allow you to seamlessly combine image data with non-image data, so you get the most out of all your data. And as always, BigML users get to focus on their business use cases, since all the infrastructure management is abstracted away by the platform. And finally, you have the choice between coding with our bindings and REST API, or using the no-code, point-and-click BigML dashboard interface when you're building your machine learning workflows. With this brief introduction, I'd like to pass it to Charles Parker, BigML's VP of Algorithms. He will share with you the technical details of our object detection implementation and show you how it works with a live demo.
Thank you very much, Atakan, for the introduction. I'm going to dig in a little more to the technical side of the object detection implementation that BigML is bringing to production today. And specifically, I'm going to talk a little bit more in detail about how the algorithm works, and then we'll go into a demo of the various parts of BigML's object detection offering. So first of all, let's talk a little bit more specifically about what object detection is. What you're doing when you run an object detection algorithm is you're looking for a specific area in the image that contains an object, and you're trying to identify the class of the object. What comes out of the object detection image is a set of coordinates, a class, and a score that's given to the box is the probability, which is the probability of both of the factors. That is, does this box contain an object, and is the object of that class? So even if the model thinks there's an object there in a particular region, it may not give that object a high score because it doesn't know what it is. So these object detectors are specifically designed to detect some finite number of things, not anything that could be in a box, but some strictly discrete set of classes. Just an aside here, while we typically visualize the prediction as a box, and while a box is kind of the traditional way to visualize these predictions that come out of these models, this is just for convenience. The parameters, which are the bounds on this rectangle, the x and y min and max of the coordinates of the box, those could also be an ellipse, or it could be a diamond. All you're getting is, again, the bounds of the containing rectangle of the shape. And what this means is that these boundaries are unlikely to be pixel accurate even when the image is axis aligned, even when the boundaries could be pixel accurate. So you see in the image we have this book where the book is a rectangle. Those bounds could be a lot tighter, but that's not what these algorithms are designed to do. These algorithms are designed to give you an approximate location of the object that has been detected and an approximate estimation of the size of the object in pixels in the image. So let's talk a little bit also about what object detection isn't. Some of the things that object detection isn't are classification. So if you want the entire image to be assigned a class, you want to know what the class of the entire image content is, that's just image classification, which is already available on BigML. As I said a moment ago, object detection does not give an idea of exactly which pixels in the image are part of the detected object. It only gives you this approximate size and approximate location. If you want to know exactly which pixels are are part of the given object, you want something like image segmentation or semantic segmentation. These are the algorithms that will tell you exactly what pixels in the image are part of the object. And these aren't available at on BigML yet. These algorithms are generally slower to train and slower to run. And so we have these algorithms, we offer these algorithms first because these algorithms, even though they don't give you that detailed information, they're much faster, and generally they produce outputs that are very reliable for the outputs that they produce for this approximate location, approximate size. Finally, object detection on its own doesn't find specific parts of the object being detected. Algorithms that do that are often called key point detection for articulated objects. This is sometimes pose estimation. So if you've got an articulated object like a person, where the different parts of the object can be configured differently in spatial relationship to one another, this is called pose estimation. It is possible to do this with object detection. You could label the person's 2 hands and the person's 2 feet and their head, and you could try to track all of these separately. And this would be a form of pose estimation, but it isn't designed to do this. So in a pinch, you can use object detection to do some of these tasks where you identify the parts of the object if you're willing to label all of the parts of the object as separate objects themselves. So how does BigML allow you to perform object detection? The basic idea here is first that we've introduced a new optype, and an optype in BigML is again a type of data that you can upload to the platform. So you can see we have the optypes that we're used to here, numeric and categorical data. Of course, BigML also handles date, time, and text data natively using some simple transformations. And then more recently, we've added images and their associated paths as date types. And now for this release, you can see on the bottom of the table in bold, we have regions. And what regions are a list of 5 tuples with the label of the object, and then it's the coordinates of its bounding box, the minimum and maximum X and Y values. And so as an example of this, you see there on the bottom right, we have a list of 2 labels for a given object. One is a cat, and it's located at these coordinates. One is a dog, it's located at these coordinates. The coordinates that we give here are relative to the image itself. So when we say the X coordinate is 0.5, we mean it's halfway across the image. When we say the Y coordinate is 0.1, we mean it's 1/10 of the way down the image. We also accept pixel coordinates. You can upload whatever's most convenient to you, but internally, BigML represents these labels in terms of these relative coordinates, coordinates relative to the image size, and that's what we output when you make a prediction. And so let's see that in action a little bit. Of course, one way to do this is to come to the platform with a bunch of labels that you've already made, either by hand or with another tool, and you can do that. So you see in this folder, I have a bunch of images, and the images in the folder are of potholes. So this is an example of a monitoring application, a nice little monitoring application where you're driving a car down the road. Maybe you have a camera that images the street as you go down the road, or maybe multiple cameras that image the street, and you get images out that are images of potholes on the street. Well, rather, they're images of the street, and your job is to detect where and how many potholes are in those images. So you can see I've got a bunch of images here, and then I've got this JSON file that's going to tell us the labels for this data set. And so in this file, you can see it's a simple JSON file. It's a big list, and the elements of the list are dictionaries or JSON objects with the file name as one of the properties of that JSON object, and then a list of boxes as the other property. And you can see each member of the list is the coordinates of the box and the label itself. This data set happens to have only one label, the potholes on the street, but of course, in general, you could have many labels here. And as we go down, we see that this object that we're looking at here, or this image that we're looking at here, has many objects labeled in it. If we go down to the next one, we see that this image here only has 2 labeled potholes. And we'll see some that have 1, some that have more, some that have less. But this is what the image file looks like. This is one way you can upload images to the platform. And so if we put all those, that JSON file along with all of the images that it references into a folder like we have here, and we just zip up that folder, we can upload that entire zip file into the platform, and we get a data source with a bunch of associated composite sources, just like we do for any other BigML resource or any other data that you want to upload into the platform. The data gets created as a source. If there's a bunch of images in the data, those are considered parts of the composite source. So you get underlying sources for each image. And you get a file like this. So if I go into my pothole data set, here I'm uploading a new copy of it. This is a copy I've uploaded earlier. Here's the pothole data set. You can see it has just the 3 files, or the 3 fields, the file name, the boxes, and then we have the image ID, which is the address of the BigML source. If I go to images here, I can look at my labels, and if I like, I can play with the labels. So here, this image has a bunch of potholes labeled. Maybe I don't like one of those potholes, so I can go to regions editing over here. I can remove one of the potholes. Maybe I think I see another pothole somewhere else, so I can give a couple of clicks here and create a new pothole. So basically, you're allowed to edit the regions that you bring into the platform as you see fit. Also, you could it's very much fine to upload a data set with no labels, a collection of images that are not labeled yet, and use this interface to label all of the images. And we've done a lot of work so that this can be done asynchronously. This can be done via the API. This can be done by multiple users, all working in parallel. So all of that is possible on this web-based labeling tool. If I go to a different source here, a different data source that I've uploaded earlier, this is an image of chessboards. You can see that if I look at some of my images here, they get rather more complicated because now we have a bunch of different labels in this data set. We have a label for each possible chess piece. And if I look at one of these, you can see I've got a whole bunch of labeled chess pieces here, but I've missed these captured pawns down on the bottom here, and maybe looks like this is the black bishop maybe that I've also missed out here. So if I wanted to label these, I could click my label here and label my new black pawns on the bottom. So again, just an example of how this works, how you can edit regions, how you can add new regions, remove regions using this labeling tool that we're offering as kind of a first-class part of the platform. And so what do we do after that? Now we have a labeled data set. We've constructed those labels. Either we've brought them in from somewhere else, or we've constructed them ourselves using the BigML interface. What do we do with that? Well, we have the usual workflow for machine learning. So the more things change, the more they stay the same. We're going to do the same things, all of the same things that we usually do when we're doing machine learning. So we upload the zip file. It has some images in it. We maybe label those images, create a BigML data set from those images. Again, a data set is the process of just serializing that data into the BigML platform so that it can be accessed quickly. And then we'll split the data set into a training and test data set. We'll train a deep net in this case. The only algorithm that we have that can do object detection right now is deep learning based. And so we're going to, or the suite of algorithms that can do object detection right now are deep learning based. And so we'll always train a deep net to do our object detection. And then we can evaluate that deep net on our test data set. And we can be somewhat sure that if the data set was constructed properly, that we get a nice estimate of how we expect that model to perform in the future. And so what does that look like in the BigML interface? Once we've uploaded our source, we can go to create data set in the usual one-click data set way. If I go over here, there's a data set that I've already created and I've already split into training and test data sets with this pothole data set. And I've already trained a deep net from this data set. Deep net training, even with GPUs, these object detection models can take a little while to train. In our case, depending on the difficulty of the problem, this can be anywhere from 10 minutes to several hours if the problem is very difficult, if you have a lot of labels and a lot of images. So I've trained these ahead of time. And if we look at the deep net that I've trained ahead of time, you see immediately we get a visualization here that shows us the performance on held out data. And so here at the top of this interface, at the very top of this interface, we have some statistics about how well the model performs on the held out data set. And again, held out data set is data set that's held out in training. We train the model on the training portion of the data set that we pass in, and then we hold out some data just to see how well we're performing and to decide when the algorithm should stop running, when it's at its peak performance. And so on the top of this image view here, we have all of the images where we correctly identified all of the objects in the image. You can see here, there's just the one pothole in the foreground, and we've correctly identified that. There's this interface at the side here where we can specify what we want to see. Do we want to see the ground truth regions? Do we want to see the predicted regions? You can see here, if I show the ground truth region along with the predicted region, you can see that the boxes match up fairly well. And then if we want to look at images where we didn't perform quite as well, you can see a lot of these images are cases where we either have a whole bunch of potholes in the image or the images are a bit strange in some way. You can see this one has a news chyron on the bottom. This is a image with a lot of potholes in it. You can see that if I enable my ground truth regions here, it says there's these 4 potholes that I missed. In reality, this image may not have been labeled very well because these look like a lot of other smaller potholes in the background here. But this is the basic idea, is that you get immediately when you train the deep net, you get a summary of its performance. This isn't a summary that can be used to replace an evaluation. To do a proper evaluation for the model, you need a properly held out test set that the model didn't even look at while it was training, whether to do validation or otherwise. But this gives you kind of a good first approximation of how we expect the model to perform. So you can see recall precision around 50%. Again, what this means is that we detect about half the potholes in the data set, and we also introduce about as many false positives as we detect. So let's talk a little bit more about what's going on under the hood when we create one of these object detectors. Basically, the way these algorithms work, the sort of algorithms that we're deploying to do object detection on BigML, is we break the image into a rough grid of cells, and by rough, I mean each cell contains a pretty good chunk of the image. And then centered at each, so we're looking at a grid of like 16 by 16 or 32 by 32 over an image that can be as big as 512 by 512 pixels. So a pretty rough, a pretty coarse grid over this fairly large image. And then centered at each cell, we're going to consider a number of bounding box proposals. What we mean by bounding box proposals is at each cell, we're going to consider a number of boxes that we think might contain an object. And so for each box in each cell, we try to predict the following things simultaneously. First of all, whether or not there's an object inside that takes up most of the box. Also the class of that object, and finally the adjustments needed to make the box fit properly around the object. So you can see this rectangle here, the kind of second largest rectangle in the Y dimension. That rectangle is the best match for this chair here. That rectangle, when it's centered at this grid cell, is the best match for this chair here. So we would label this particular rectangle at this particular location. We would say, yes, there's a chair inside. The class of the object would be the chair. And we would also have some adjustments to this box that would make it fit the chair properly. So for example, you can see that on the right side of the chair, there's quite a bit of space. And so we would say something like, this box needs to be a little bit narrower. and it needs to move over to the right a little bit in order to properly fit the chair. And so these models are simultaneously trying to predict all of these things for every single grid cell in the image. So no matter where there is something in the image, the idea is that one of these bounding box proposals will fit. Now, where do we get this set of rectangles from? We don't just make up a set of rectangles and say, oh, probably if we put this set of rectangles at each location in the image, probably we'll cover all of the objects. Instead, what we do is we actually look at the size and shape of the regions that you specified in the training data. So, for example, in that chess data set, all of the regions that you specify are tiny because all of the pieces are tiny relative to the board. And so it's only going to look for tiny things in the image. It's only going to hypothesize rectangles. It's only going to propose rectangles that are very small, much smaller than this for chess pieces. On the other hand, the potholes, in the potholes data set, there were a few potholes that you saw in the foregrounds of images that took up quite a large portion of the image on the order of the size of these rectangles. And so in that case, in the pothole data set, the bounding box proposals will be much larger because there's those larger rectangles. In the pothole data set, there's also some very small rectangles, and so we'll still maintain some very small bounding box proposals. And the way we do this is a bit technical, but basically we take the list of rectangles and we perform clustering on them, and then we take the centroids of those clusters as our bounding box proposals. So that leads us to some caveats. When is this not going to work? And this is always kind of the most fun to talk about when you get to the limitations of these algorithms, because that's the point when we as machine learning practitioners get to really know what we're doing, in a sense. We're not just throwing an algorithm at a problem we know it can't solve. We're trying to find the best algorithm to solve the problem that we know is going to work. So the usual caveats about feeding images to machine learning models still apply. If you fed a bunch of images of little trees like this into your training algorithm and all of the images that you fed in were very sharp, if you feed in a blurred image, it's not going to work. It's going to assume that this is not a little tree because little trees are never blurred in the world of the algorithm. In the world of the algorithm, little trees are always sharp. And so it will, in many cases, assume that a blurred tree is not a tree at all. Similarly, with negative images, this is something that often surprises people. If you just if you have black and white images, you just swap white for black everywhere in the image, this will completely confuse a lot of algorithms, again, unless you've trained on both black on white and white on black images. Why is that? Because if you have, say, these birch trees labeled in your image, and the birch trees are white in all of the images that you've labeled, then when you feed it a negative image, those same birch trees are going to be black, and your algorithm is going to say to itself, oh, birch trees are never black, these are certainly not birch trees. This makes perfect sense in the world of the algorithm, but it's something that can be surprising to people, especially when you get to things that people are very used to identifying, even in situations like this. So a good example is if you have an algorithm trained on the classic digit data set where you're training it to recognize handwritten digits. The canonical version of that data set is white pixels on a black background. The digits are written in white. If you swap those colors so that the digits are written in black on a white background, the algorithm, if trained naively on data that's only white on black, will completely fail. And to you, the human, you look at that, you say, no, that's still a 2. You've just swapped the colors. That's obvious. But to the algorithm, what it's trying to identify is a 2 that looks like the 2 that it usually sees. The 2 that it usually sees is never black. And of course, this is not a 2 to the algorithm. And so another one of these kind of strange cases specific to bounding box detection is in our chess piece case, where, as I said before, all of the bounding boxes that you see in training in the chess piece case are very small because the chess pieces are all very small relative to the size of the board. And so if you feed it an image like the one we have in the bottom right here, this king that's very large with respect to the rest of the image, very large with respect to the board in the background, the algorithm will again completely fail to detect this king. Why is that? It's because the algorithm thinks that black kings are very small, because the only black kings it's ever seen are very small relative to the board. If you pass it one that's very large relative to the board, this is not the sort of black king that the algorithm has ever seen before. And so, of course, it's not going to decide to label this thing a black king. Again, the way to fix this is to just feed that sort of data to the algorithm. So if you expect to see chess pieces both from far away so that you're viewing the entire board and also from close up, you need to feed the algorithm examples of the image with the chess piece imaged more close up. And then finally, the last thing I'm going to talk about in this little section is what if we need more power? So the algorithms that we use on BigML.com on the public deployment of the architecture are modest in size, and the reason we made that choice is because they run faster, they train faster, and you don't need any kind of specialized hardware to get them to run fairly quickly. You can still do several predictions per second with these algorithms, even if you don't have a GPU. So that's nice for the public deployment, but there are cases where if you're an individual who has access to thousands of labeled images, or maybe tens of thousands or more of labeled images, and you've got a particularly difficult problem. A good example of this is the license plate reading problem that we have deployed for a beta customer in BigML, where you have many classes, all possible digits, and a few other markings on the license plate are separate objects to detect in the license plate reading problem. And many of them occur on many of the license plates. Most license plates have, many characters on them, many markings on them. And so in that case, we happen to have thousands of images because the toll provider we're working with is constantly providing us with images. So it's easy for us to train a much larger model because we have the data to train it properly. So if you have that case where you have specialized hardware to run one of these larger models, you have the data to train one of these larger models, this might be the case where you want to opt into a BigML private deployment, where we can provide you with a version of the platform designed to train and run these larger object detection models, which generally perform better if you have the requisite data. The thing, of course, that we want to do once we train these object detectors is to actually go and make predictions with them. And making predictions with the object detectors is the same as making predictions with any other BigML algorithm. You can go to predict, and when you go to predict, it gives you a form to fill out with the input data. In this case, you just need an image, and so we can drag an image onto the interface. Here I have an image of potholes ready. I'll just put it here. You can see I have an image with a nice pothole in it. And if I go to predict, I can get a prediction of the potholes for this image in the interface. Now, of course, because this is BigML, this interface is built on our own API, and so you can do this all from the API as well. If I lower my score threshold here, so here I'm saying I only want boxes that have a score of 50% or above. If I lower that to 10, and I repredict, then it'll start pulling in more and more things that might be potholes and might not be potholes. And that's kind of the beauty of the score threshold, is you get to decide how picky you are about the things that the detector is detecting. And in this case, when you lower that threshold, you can see that it picks up several areas in the road over here that are probably not potholes. It's only saying 10% pothole for these two small areas here, but they are areas of the road that's pretty rough. And then we get to the final step in our data workflow for object detection, which is evaluations. So evaluations for object detection, if you read the object detection literature, the academic literature, you'll quickly see that they work a bit different from your standard classifier evaluation. So our standard classifier evaluation, we're used to this confusion matrix over here, where we have true positives, true negatives, the correct predictions on the diagonal of the matrix here, and the off-diagonal predictions are various flavors of wrong. There's the false positives, where you say that something was there and it wasn't, and there's the false negatives, where you say that something wasn't there and it was. So for object detection, this true negatives cell can be a little bit misleading. So in object detection, like I said, there's many possible bounding box proposals at many different locations in the image. You can see very quickly that gets to thousands if you think of a 32 by 32 grid, and at each point in the grid you have several bounding boxes that you're trying out. We very quickly get to a lot of rectangles, and in the vast majority of those bounding boxes, there's going to be nothing, just because of the nature of object detection. Most of the time, when you're making a prediction at some location in the image, nothing is there. In the pothole data set, most of the images of the road are not going to be potholes. Most points on the road in every image are not going to be potholes. As such, when we evaluate these algorithms, we don't typically take true negatives into account in the usual kind of confusion matrix sort of way. We don't rely on metrics that rely on the true negative count specifically, because then the evaluation of the object detector would be dominated by how many of the no object rectangles that it managed to say no object for. This isn't really helpful, right? It's sort of like evaluating Google search results. If you're not really concerned about the 7 billion web pages that aren't relevant to your query. What you wonder is if the top 10 web pages were relevant to your query. And so typically we don't rely on these metrics that involve true negatives. Instead, we rely on things that are based mainly on precision, recall, and the combinations of thereof, which are things like the F1 score and the average precision. These are things where you don't need an explicit count of true negatives to create a value for that metric, to compute a value for that metric. But there are some things that are the same between classifier evaluations and object detector evaluations. And one of those things is the ability to change the score threshold for the model and see how that impacts the count of true positives, false positives, and false negatives. So if I go back here, I've done an evaluation on my pothole data. Here is the default score threshold of 50%. You can see I have precision and recall of about 70% and about 50%. And then moving around the score threshold, I can move the precision recall cursor around here and get different versions or different values for precision and recall. You see I have an absolute count of the objects that are in the data set here, and the false positives I've detected as well. If we look at this object, for example, here I believe we're getting everything right. Yeah, we're getting everything basically right in this image. So there's the ground truth potholes, and here's the detected potholes. And then if I bring the score threshold way down, for example, I'll start to pull in things that are unlikely to be potholes. So you can see here, I've pulled in a couple of low scoring rough areas in the road that are not labeled as potholes at the top here when I lower that score threshold. So these are just examples of the predictions that go with the evaluation. You've got the usual score slider to trade off between precision and recall, as you do with other evaluations. The other thing we have to worry about here that's peculiar to object detection predictions is the notion of correctness. So in classifiers, it's fairly obvious if you've made the correct prediction or not. If the prediction you make matches the class of the object, then it's right, and otherwise it's wrong. In object detection, we don't get so lucky, because rarely do our ground truth bounding boxes line up exactly with the boxes that we predict. Clearly, if the boxes align exactly, then the prediction is correct in any case, but almost always that doesn't happen. It's just vanishingly unlikely that you'll get pixel by pixel matching versions of those boxes. And usually that isn't important anyway. So if you've got a set of bounding boxes that mostly overlap, like we do in the middle here, we can basically consider that to be a correct prediction in most cases. If you're not concerned with the exact overlap of the boxes, if you can tolerate a little bit of jitter in the overlap, then you'll say, oh yes, we've basically detected the size and location of the object if the truth looks like this and the prediction looks like, if the truth looks like the box in green, the prediction looks like the box in red. And so how do we formalize that? We use a quantity called intersection over union, which pretty much everyone else uses. And the basic idea here is that if the ratio of the intersection area of the two boxes and the union area of the two boxes is large, then you've got a lot of overlap. If the IOU, and essentially we set a threshold here and we say if the IOU is above this threshold, then that means that the prediction is correct. And if the IOU is below the threshold, we label the prediction incorrect. So in some cases, this here, where we have an IOU of about 0.4, in some cases, this may be good enough, right? You've identified the correct object. You've got it sort of in the correct location. The size is wrong. But for your purposes, if you're just counting objects, for example, then that might be enough. Here, with an IOU of 0.73, this seems like it's probably enough in most cases. And clearly here, you've got an IOU above 0.9. That's going to be a good enough prediction in almost every case. There's no, it's hard for me to imagine an application where you need a more precise alignment than this to consider that prediction to be useful or correct. And so what is the threshold that we set? The threshold that we set, essentially, we do it several times for several different thresholds, and you can pick which threshold you're using based on the domain, based on how correct you need the predictions to be. So here, for example, you see the IOU threshold. This is what the precision recall curve looks like for an IOU of 0.5. So that's, I would say, maybe the most often used IOU threshold when you're evaluating these object detection algorithms. If you go to these higher levels, you will necessarily get an evaluation that looks worse because you're being picky, more and more picky about what a correct match looks like. And you can see if we go all the way up to 0.9, almost none of these predictions are considered correct just because the bounding boxes don't line up exactly. If we go to another evaluation, here's a similar evaluation for the chess pieces. You can see that the evaluation for the chess pieces is a bit more complex. We only see one precision recall curve here, but if we go to the summary, we can see we get a separate precision recall curve for every single object class. And so if I go to white pawns here, for example, I get this curve. I can pick different curves from here as well. Here's the curve for the white rook. And I can move these sliders and see what precision recall trade-offs can be made for all of these other pieces as well. And again, going to these higher levels of precision, these higher levels of IOU threshold, I get pickier about what I want to see for a match, and the evaluation gets worse as I go up the IOU scale here. So to wrap up here, that's in a nutshell, that's what we're offering and for object detection at BigML. Again, a pretty comprehensive end-to-end solution, all the way from labeling to making predictions. But still, that's not all. As Atakan mentioned, there's a number of other reasons to use BigML other than the fact that we offer an end-to-end solution, we take care of all the infrastructure concerns for you, and we have this nice user interface that allows you to do this using no code. There's still the matter of composability. And so often in machine learning problems, you don't have something that's so straightforward as you put in an image, it tells you the objects, and then you're done. You're able to consume those object predictions with no further avail. This sometimes isn't true, right? Sometimes you have problems that are a bit more complex. So for example, suppose you have a basic list of things you'd like to detect, but you know that list isn't exhaustive. And a good example of this is if you're doing monitoring of a highway. So if you're doing monitoring of a highway, you've got a camera looking down on the highway, there might be many different objects, foreign objects, that make their way onto the roadway. Most of the things you see on the roadway will, of course, be cars, but occasionally you'll see a person crossing the roadway. You might see a bit of debris on the roadway, like something that dropped off of a car. You might see a tire that blew out on the roadway. And so if you would like to detect foreign objects on the roadway, you don't get to have an exhaustive list of things that you might see. You know some of the things that you might see. You might see tires, you might see people, you might see bits of a car, but you won't be able to account for all of the possible things that could have fallen off of a car or out of a car or have been tossed on the roadway. So you need a detector that will work generally for anything that might come onto the roadway. So the solution here is, instead of training an object detector that looks for people and tires and debris of other kinds, you just train an object detector that detects a generic thing. So you train a one-class object detector, just like our pothole detector, that will fire every time it sees anything on the roadway, presumably anything that's not a car. And then you can crop out those, as you make detections, you can crop out the detected objects, because we know the coordinates in the image of each detected object. You crop out those detected objects, and then you pass the crops to both an anomaly detector and a classifier, just a regular image classifier and a regular image anomaly detector, just as we did in our image release. When we talked about anomaly detection in our image release, we talked about classification in our image release. We can train a classifier and anomaly detector based on these cropped images where the crop contains the object you saw on the roadway. If it's a known object, that means the classifier is going to fire with high confidence on the class of that object. So you'll know if you're looking at a person, if you're looking at a tire, if you're looking at something you commonly see. If it's a strange object that you've never seen before, then the anomaly detector will fire with a high anomaly score and say, hey, this is something we've never seen before. Ignore the classifier. It doesn't know what it's talking about in this instance. So you get from the anomaly detector, you get to know the classifier competence, and then also you get an object detection model that's a kind of thing agnostic, if you want. It's looking for anything on the roadway, not just things of a specific class. And again, the beauty of doing all this in BigML is this can be scripted in BigML and all run on the server side. Or you can use our API to do all of this locally, managing the calls to the API from the client side. But what you don't have to do is use separate imaging libraries or separate tools, cobbling things together to have a full solution operating in production. You can do this all on BigML. So to sum up, and to kind of give a final pitch for BigML, is that this is object detection, yes, which is out there in open source libraries, and there are other surfaces that offer pieces of this solution, but this is object detection the BigML way. And so with the BigML deployment, you get all of the usual benefits of using BigML. So first of all, everything is mutable, traceable, and composable. Composable is what we just talked about. You can put things into workflows using all of the rest of BigML to complement the object detection feature. Also, immutability and traceability. If you want, you can always, if you need to, you can always follow the models that you train all the way back to the training data. So again, I always like to show this little tree. When we're at an evaluation, we can always go back to the data set from which the evaluation is created. We can go back to the model that created it. And then furthermore, if we're at the model, we can always go back to the data set that created it, always go all the way back to the data source that created the model. So you can go, for any model, you can go back to the source. You have a guarantee that it hasn't changed. And so you can look at those, you can inspect individual images that were used to train that model and make sure the labels are correct. You can rectify errors and train a new model by duplicating the source and making it editable again. But everything lives forever on the BigML platform unless you delete it specifically, which is great for cases where you need to audit models, you need to do record keeping, you need to review the models you have in production and know exactly the data that they were trained on, know exactly where those models came from. And then, of course, everything is available via the API and downloadable. Everything that I showed you in the interface is programmed on top of our API. So you yourself could do any of that. You could have your own prediction interface that ran on top of BigML's API. You could program your own labeling interface that runs on top of BigML's API. There's no secret API calls that we use internally that we don't offer to you externally. So everything that we can do in the UI, you can also do via the API. Models are live via the API endpoint. As soon as they're created, you saw that I can just create a model and immediately I can go to that model and start making predictions at scale on BigML hardware. And then finally, models can be downloaded and run locally. And in this case, especially if you use our Python bindings, you can just download the model, instantiate it locally in the Python bindings as you would any other model, and you can be immediately making predictions in Python or making predictions on edge devices as you need to.